Good morning everybody. Today we will discuss about ADI scheme and TDMA. ADI is alternate direction implicit. This is alternate direction implicit scheme and tridiagonal matrix algorithm. Now, in the last class, we have studied about implicit schemes, and specifically we have nurtured with Crank-Nicholson implicit scheme. Now, that was for one-dimensional unsteady state conduction. Let us consider two-dimensional heat conduction equation given by du dt equal to alpha d2u dx2 plus d2u dy2. Again, for the generality we have written u, but u signifies temperature here. So time derivative of u is time derivative of temperature equal to thermal diffusivity into del 2 temperature del x2 plus del 2 temperature del y2. U signifies temperature. We can straightforward, if we write explicit scheme, we can write uij at n plus 1 minus uij at n divided by delta t equal to alpha. Then within bracket we can write the central difference, finite difference quotient of u in x direction. That means ui plus 1j minus twice uij plus ui minus 1j, all are at nth level, divided by delta x square. This is central difference in x direction, and this is central difference in y direction. uij plus 1 minus uij plus uij minus 1, all at nth level. Let me repeat here. U signifies temperature here, and alpha is the thermal diffusivity. Now, explicit scheme, as we have seen in the case of one-dimensional heat conduction equation, can be explicitly evaluated at the point of interest, that means at ij, with respect to the point of interest and its neighbors at the previous level, but all the values are known. Whereas when we use Crank-Nicholson scheme, we write in the same way uij n plus 1 minus uij n by delta t equal to alpha by 2 delta x square delta y square. These delta x and delta y, these are operators, and they are operating on uij at n plus 1th level and uij at nth level. Since they are operating, they are supposed to operate on the dependent variable, but they are operating on the dependent variable at two different time levels, and we are writing them in additive manner. So we are dividing it by 2. So basically this is averaging out n plus 1th level and nth level. So alpha by 2, then central difference operator operating on in x direction, operating on uij at n plus 1th level and nth level. Then again central difference operator in y direction. This will apply on uij at n plus 1th level and nth level. So we have shown here this operator, central difference operator in x direction. That means simply central differencing the dependent variable in the x direction. Similarly, del 2y is the central difference operator in y direction. It discretizes the dependent variable in y direction following central differencing, and it is having second order accuracy. So this method is a two-step scheme which proceeds in two halves of each time step. This results in two equations. One basically operates between n to n plus half level. Another is basically n plus half to n plus 1th level. So when we progress from nth level to n plus half level through a time step delta t by 2, we can see we apply central differencing operator on the dependent variable at central differencing operator in x del x2. We operate it on the dependent variable at n plus half level. Whereas in the other direction, it is operated at nth level. This is also central differencing operator in y direction, but it applies on the dependent variable at the known time level. And this is the way we proceed up to n plus half. Having progressed up to n plus half, we go from n plus half to n plus 1th level, and there again through time step delta t by 2, and there we can see that central differencing operator in x direction is applied on the dependent variable at n plus half level, and central differencing operator in y direction applied to the dependent variable at n plus 1th level. When we apply in the first step, n plus half is unknown. It is on the left hand side. It is also on the right hand side, because we can see that central differencing operator in x direction applied on the dependent variable at this unknown level. And again, from when we having known values at n plus half level, when we progress to n plus 1th level, then on the left hand side we write uij n plus 1 minus uij n plus half by delta t by 2. But on the right hand side we express uij, that means the dependent variable at n plus half level is discretized form, central difference discretized form at n plus half level. So dependent variable is discretized in x direction through central differencing, and it is at n plus half level, which we have known already from the previous step. But we write again the dependent variable at n plus 1th level, which is unknown in the second step. And this is again central differencing operator in y direction, but the dependent variables are written at n plus 1th level, which is unknown. And on the left hand side we can see the dependent variable is unknown at n plus 1th level. And that is how the implicitness comes when we express the discretized form of dependent variable on the right hand side in terms of unknown quantities. N plus 1th level values are not known. Similarly, in the first step, n plus half level values are not known. We see that here every step is an equivalent implicit scheme. At each step, a tridiagonal matrix is obtained that can be solved by Thomas algorithm. So, if this is the plane where we have the dependent variable distributed, here it is temperature, and a grid has been drawn, and then when from we are, and this is these are x and y directions, and this is time direction. So in time direction, here we progress n plus half, and then we write, as we stated earlier, we will write uij at n plus half minus uij n divided by delta t by 2 into alpha. This is central differencing on uij at n plus half level, and this is central differencing on uij in y direction at nth level. All nth level values are known, but n plus half level values are not known. And then we can rearrange these equations, in this form. And before that, we just define a equal to alpha delta t by twice delta y square, and b equal to minus alpha delta t by twice x square. A equal to minus alpha delta t by twice delta y square, and b equal to minus alpha delta t by 2 delta x square. So here we can see, we can write b into ui minus 1j plus 1 minus 2b uij plus b into ui plus 1j, all are at n plus half level. And we are supposed to determine uij, but uij cannot be determined alone. It is expressed in terms of ui minus 1 and ui plus 1j and ui minus 1j, so at n plus half level. So n plus half level, we cannot determine uij alone. We have to express uij in terms of its left neighbor ui minus 1j and its right neighbor ui plus 1j. On the other hand, in the right hand side, we can see what we write: uij at nth level, this term comes here, minus a uij plus 1 minus twice uij plus uij minus 1. Within this a, basically this alpha delta t and twice delta y square, these are absorbed, and all these are known. Now at n plus half level, we can anchor at each j station. For each j value, we can vary I equal to 1 to the maximum point. 1 to number of points are from 1 to I max. So here we have written 2 to I max minus 1. Why we have written 2 to I max minus 1? Because when we write, u2j, this will be u1j and this will be u3j. So u1j will be the boundary condition. Similarly, when this ui will be I max minus 1, this I max minus 1j, this will be I max minus 2j, and this will be I max j. So, and I max j will fall on boundary and its value is known. So, we will basically vary I from 2 to I max minus 1 for each j. So, we will vary j equal to 1, of course, all are boundary conditions. J equal to 2, we fix j parameter, then vary I from 2 to I max minus 1. That means we get it, complete this matrix equation. And if we invert this matrix equation, after varying it 2 to I max minus 1, we will get a tridiagonal matrix, and after inverting that, we will know all the values. Then we will go to j equal to 3, then we will go to j equal to 4, and this way we will complete all the j points. This is called j sweep. Now in the subsequent second step, we will write uij n plus 1 minus uij n plus half divided by delta t by 2 equal to alpha. Here central difference operator on the dependent variable in x direction at n plus half level. And here again central difference operator on the dependent variable in y direction at n plus 1 level. And n plus 1 level values are not known. Now these values are all the values at n plus half level known after completing the j sweep. So these values are known. So these known values are moved to the right hand side. And unknown values at n plus 1th level values, they are moved to left hand side. And now we can write a u I j minus 1 plus 1 minus 2a uij plus a uij plus 1 at n plus 1th level. These are all unknown. We are supposed to determine uij, but uij at n plus 1th level alone cannot be determined. They are always expressed in terms with or together with their neighboring points, ui j minus 1 and ui j plus 1. So if we vary j equal to 2, we'll get u I1, u I2, u I3, then j equal to 3, j equal to 4. So for here, we'll keep I values constant. For example, at I equal to 2, if we vary j equal to 2 to j max minus 1, we will complete the sweep. That means we'll get a tridiagonal matrix, and if we invert that, we will get at keeping I equal to 2 constant at all j values for I equal to 2. Then I equal to 3 will get all j values, and for each I will get a tridiagonal matrix, we'll invert that and we'll get values of all j's. So at each I we'll get a tridiagonal matrix from where we'll get values of all j's. So this way, varying I from 1, 2, 3, 4, this way we'll be able to complete the calculation. And having completed that, we have now come from n plus half to n plus half to n plus 1. That means we have completed our calculation from nth level to n plus 1th level. And this second order accurate in space and time, and this is called alternate direction implicit scheme. It is implicit in alternate directions. Once it is implicit in I direction, another t by 2, it is implicit in j direction. So Taylor series expansion around uij n plus half in either direction, So this uij n plus half in either direction means uij n plus 1th level, and from here uij at nth level. So this can be written by the basically Taylor series. This is in the forward direction, this is in the backward or rearward direction, and from there if we now try to write uijn plus 1 minus uijn from these two Taylor series, we will get del u del t into delta t plus 2 by factorial 3 del 3u del t3 del t cube del t by 2 cube. So we can see from here, if we express del u del t, this is inherently dropping the first order term, so in the truncated series. So this is second order accurate in time. That is why we are saying that ADI scheme is not only second order accurate in space, this is also second order accurate in time. Now this is about our implicit schemes. We have discussed fully implicit, we have discussed Crank-Nicholson implicit, and we have also discussed alternate direction implicit schemes. Now we will mention about a topic which is related to explicit schemes, because we are not adhering to only one type of schemes, implicit or Crank-Nicholson implicit. In some places we will see explicit schemes are more advantageous. But explicit schemes, we have to pay attention to major factor, which is basically stability. Now we'll discuss about errors and stability. There are two major sources of errors in the numerical solution obtained by approximating the PDE. One is discretization error. This is the truncation error plus errors obtained by other numerical approximations. And then round off error. Numerical error introduced for a repetitive number of calculations due to rounding off by the computer up to some specified decimal place. These errors get accumulated. The solution will be stable only if magnitude of error shrinks. As the solution progresses in the marching direction from n to n plus 1, the error has to shrink, or at the worst case it may stay at the same level, but it has to finally shrink for the convergence. So what is rounded off error? This is the numerical error introduced for a repetitive number of calculations in which the computer is constantly rounding the number to some decimal points. Depending on computer, sometimes it rounds up at 16 decimal place, sometimes it rounds up at 32nd decimal point, decimal place. Sometimes it is at 64th decimal place. So it depends on computer architecture. If A is the analytical solution of the partial differential equation and D is the exact solution of the finite difference equation, then N is the numerical solution. Difference between N, we will assume that in the when we reach convergence, basically N is equal to D. Now, discretization error is basically truncation error plus error introduced due to treatment of boundary condition, etc. This is A minus D. That means the exact analytical solution we do not get because of discretization error, which is basically truncation error plus error introduced due to treatment of boundary condition, the way first order, second order, accurate boundary conditions, same boundary condition, but it can be first order accurate, it can be second order accurate, they are applied. So these are the errors at the mathematical level, right? As I said, that A is the analytical solution and D is the exact solution of the finite difference equation. That means, it has no other error but truncation errors and the errors that come from implementation of the boundary condition. Same boundary condition can be higher order. So, but what is rounded off error? Rounded off error is we are expecting to get D always. And if we get D, we are really satisfied. But when we do the machine computation, we do not get D. What we get is N. And this discrepancy is because of round off error. So epsilon is N minus D, or you can say N equal to D plus epsilon. So what if we are expected to get D, but we are getting N because what is the difference is D is being modified or convoluted in a way through error, which is epsilon. Now this then we can write, for example, in our unsteady state heat conduction equation, D temperature, D time, D uppercase T differentiation of uppercase T, which is time, del T, del time, uppercase T, which is temperature, del T, del time, and equal to alpha del 2T del x2. Now this now here instead of T, we are expected to we are getting N. Now if we are getting N, that means we are getting here, instead of dependent variable at n plus 1th level at point I, we can write di n plus 1 plus epsilon I n plus 1 minus the dependent variable at nth level. So this is di at nth level minus epsilon I at nth level. Because n is the solution, n is the temperature here, and instead of n, we will substitute that by d plus epsilon. So n is being substituted by d plus epsilon by delta t. Similarly, alpha, again dependent variable at point I plus 1 nth level minus 2 into the value, that means temperature at I at nth level, plus temperature at I minus 1 at nth level. So instead of temperature solution, which is exact solution is D, we are getting N, and we are substituting everywhere the variable by D plus epsilon, D plus epsilon, D plus epsilon by delta x square. And the exact equation is valid for D. D is a solution, that is the exact solution. So this is given a number 3, and if that is subtracted from 2, we get a governing equation in error. So we can say that errors with the dependent variable final solution that we get, and with every point errors are interwoven this way. And this error can be a Fourier series in x and t. So we can write error is e to the power at into summation of e to the power I kmx, a Fourier series, where this uppercase I is the unit complex number. That means root over -1, and k is the wave number. So we can write epsilon m xt equal to e to the power at. This is exponentially growing component, and this is e to the power I kmx, a term of Fourier series. Finally, it stands to reason that for a stable solution, for a solution to be stable, the mandatory condition is epsilon at a given point, at any point I at n plus 1th level, divided by epsilon at the same point at nth level, previous level, so should be less than equal to 1. For the FTCS scheme, forward time and central space, for the FTCS scheme, let us examine under what circumstances this holds good. Assume that the distribution of error along the x direction or x is given by a Fourier series in x, and the time-wise distribution is exponent in t. So epsilon, we have already mentioned it earlier, e to the power at into Fourier series, and I is the unit complex number, k is the wave number, and k is basically twice pi by lambda, while lambda is the wavelength. We have written also that wave velocity is v, time period is t, then lambda is the wavelength, lambda is vt, and k, wave number, means twice pi by lambda. Since the difference is linear, when the error is substituted in equation 4, that means this equation in error, the behavior of each term of the series is the same as the series itself. Hence, let us deal with just one term of the series and write that epsilon m xt equal to e power at into e power I kmx. And then this is, we are just substituting e power at e as e power at e to the power I kmx, and this epsilon is e power at into e to the power I kmx, and this epsilon we substitute here, exactly, we express at in plus 1, I plus 1n, and I minus 1n through epsilon. And if we do that, we can write e to the power a, this is n plus 1, so t plus delta t into e to the power, this is uppercase I, which is root over -1 kmx minus e power at into e to the power I kmx by delta t, equal to alpha e power at e power I km x plus delta x, this is for I plus 1, minus twice e power at e power I kmx, this is at the point I, and e power at to the power I km x minus delta x. This is at the point I minus 1 divided by delta x square. Now if we divided both the sides by e power at e to the power I km x, on left hand side we will be left with e power at minus 1 by delta t equal to alpha, and here e to the power I km x km delta x minus 2 plus e power minus I km delta x divided by delta x square. Now this is e to the power some exponent plus e to the power minus the same exponent e to the power I km delta x plus e to the power minus I km delta x by 2. This quantity is basically cos km delta x. So cos km delta x is e to the power I km delta x plus e to the power minus I km delta x by 2. So e to the power I km delta x plus e to the power I e to the power minus I km delta x by 2 is cos km delta x. If we substitute e to the power I km delta x plus e to the power minus I km delta x by 2 as cos km delta x here, we will get cos km on the numerator. We will get basically twice cos km delta x minus 2. We take 2 outside, so this becomes alpha into 2 delta t delta x square. Delta t comes from this the left hand side, so alpha delta t delta x square is pulled out. 2 is the common factor from here, is pulled out here. Within the bracket we get cos km delta x minus 1, and we transfer 1 to right hand side. So e to the power a delta t becomes 1 plus twice alpha delta t divided by delta x square cos km delta x minus 1. Now e to the power delta t is then this trigonometrical identity. From here we can write, this is basically cos theta minus 1. We can write twice sine square theta by 2. So sine square km delta x by 2, and this becomes 2 alpha delta t by delta x square with minus sign. So now this is basically cos theta minus 1 is minus twice sine square theta by 2. So we just do that substitution as equation 9, and then we can write modulus of epsilon at ith point at n plus 1th level divided by epsilon at ith point at nth level, which is basically the ratio of errors. And if we express that, e to the power a delta t modulus of that is then mod of 1 minus 4 alpha t by delta x square sine square km delta x by 2 less than equal to, and this, if as we have already mentioned, that between 2 time step it must decrease. In the worst case it can stay at the same level, but it has to decrease for convergence. So the condition is then this is less than equal to 1. So that means this modulus of 1 minus 4 alpha delta t by delta x square sine square km delta x by 2, this modulus of this has to reduce, and this is modulus of this is called amplification factor G. So G has to be less than equal to 1. That means 1 minus 4 alpha delta t by delta x square sine square km delta x by 2. If modulus of that has to be less than equal to 1, then this has to be less than equal to 1. And then this part has to be greater than equal to 0. Then only modulus of this will be less than equal to 1. This is one condition which is always true because alpha delta t by delta x square is positive. This condition always holds. And we can get another condition also if we carefully looked at this term. This has to be mod of this term has to be less than equal to 1. So basically 1 minus 4 alpha delta t delta x square sine square km delta x by 2, this quantity has to be greater than equal to minus 1. That means it can be minus 3/4, minus 1/3, minus half, something like that. So that again the modulus will become less than equal to 1. So thus 4 alpha delta t by delta x square sine square km delta x by 2 minus 1 is less than equal to 1. Just from here, logically we can write this. Now combining these two, we can write alpha delta t by delta x square. This has to be less than equal to half. Now this is called von Neumann stability analysis. Correct pronunciation is von Neumann stability analysis. Here the error is modeled as a Fourier series and the condition of shrinking error is applied. We obtain a condition for amplification factor. For one-dimensional heat conduction equation, we get this as alpha delta t by delta x square less than equal to t by delta x square plus alpha delta t by delta y square less than equal to half. For equal delta, if delta x equal to delta y, then it is less than equal to 1/4. And this number, this stability condition, this number is called grid Fourier number. We will learn more about it maybe later. So now we will come to the third part of our lecture. We have discussed about the alternate direction implicit scheme. We have discussed about stability, and now why we were always trying to go for alternate direction implicit or Crank-Nicolson problem, because we wanted to have a tridiagonal coefficient matrix, and this tridiagonal coefficient matrix has some special advantage. It can be inverted very easily. We will very briefly discuss about that, and the algorithm which is used for that is known as Thomas algorithm. This algorithm takes advantage matrix, Gaussian matrix solver applied to tridiagonal system. It transforms the coefficient matrix into a upper triangular matrix. And the solution then, if we get upper triangular matrix through back substitution, very easily we can get the solution. So if let us consider, so this is coefficient matrix, this is unknown vector, and this is known vector. So coefficient matrix has diagonal terms d1, d2, d3, d4 up to dn, and it has immediate subdiagonal. So one element will be less. We are counting from b2, b2, b3, b4 up to bn. And immediate super diagonal, again one element will be less. We are starting with a1, a1, a2, a3, a4, an minus 1. and these are x1, x2, x3 up to xn, and right hand side all known elements c1, c2, c3, c4 up to cn. Now LU decomposition can be viewed as the matrix form of Gaussian elimination. So this is applied on basically any can be applied on any matrix Gaussian elimination, but Gaussian elimination specifically for tridiagonal matrix system, if it is applied, it finally gives us effectively one upper triangular matrix, and from there we can get the solutions very easily through the back substitution. Apply this algorithm. What we do, we just change the diagonal elements and this right hand side vector, these elements, and just these two arrays are changed, D1 to Dn and C1 to Cn. And how these are changed? D1 new is Di new is in general Di old minus Bi divided by Di minus 1 into Ai minus 1. So let us look at it. All these i's are basically indices for d's, b's and a's. So di new is di old minus bi, di old minus bi divided by di minus 1 into ai minus 1 old. These are for I equal to 2 to n. But di new is di old. So d1 is not changed. d2 is changed, like d2 new will be d2 old minus b2, we can see d2 old minus b2 divided by d1 into a1. So d2 equal to d2 new is d2 old minus b2 divided by d1 into a1. b2 old divided by d1 into a1. Now here we are writing old means just the available value. Whatever is the current available value, that is we are writing as old. And d1 new is d1 old. Similarly, c1 new is also c1 old, but c1 new from ci new equal to ci old minus bi divided by di minus 1 ci minus 1 old. So here also c1 new remains as c1 old, but from 2 to n ci values change this way, c1 old minus bi divided by di minus 1 into ci minus 1, and this is the most recent value available is the old value. And let me repeat, d1 new is d1 old, but di new is di old minus bi divided by di minus 1 into ai minus 1 old, and this is for I equal to 2 to n. And this old means the latest value available in the array. So the system is LU decomposed as we have modified the right hand side. All we need to do is to back substitution using U, that means the upper triangular matrix contains only A's and the modified diagonal matrix by xn equal to cn by dn is the last element, and the term of unknown column matrix x1 to xn. Xn is first determined, then we go to n minus 1, n minus 2, and up to 1. So xk is, this is back substitution, ck minus ak into xk plus 1 divided by dk, k equal to n minus 1, n minus 2, n minus 3 up to 1 back substitution. Basically, I am giving you a pseudo code for summarizing these steps. How to find out updated D1 and then D2 to Dn, updated C1, then C2 to Cn, and then back substitution xn, xn minus 1, xn minus 2 up to 1. See, this is a pseudo code within a do loop. Do I equal to 2 to n. This is basically for 2 to n. R is bi by di minus 1, and this is di, that di new actually is old di minus r is given by this into a I minus 1. And again, C1 is known, C1 doesn't change, but from C2 we can write then Ci equal to Ci minus R is this into Ci minus 1. So D1 and C1 doesn't change, but D2 to N changes this way, C2 to N changes this way, this is, and the do loop ends this way. And then through back substitution, xn is cn by dn, and then I equal to 2 to n. We do the back substitution through another variable, j equal to n minus I plus 1, and this stands for back substitution, and do loop ends, and we get up to x1. Thank you very much for your interest and for your enthusiasm to listen to the lecture. Thank you.